kind of here and there. We need to talk about two important types of waves. When we talk about waves have crests and troughs. We talked about the longitudinal waves like a slinky. We talked about the transverse waves going up, down, front, and jump rope. So kind of remember all that. The two types of waves I want to talk about are sound waves and generally called light waves. So I'll talk about sound waves today and light waves only on Wednesday. So sound waves, I already mentioned, I think it's so amazing. Sound waves, unlike light waves, actually need a medium to travel through. And I've got a little video to kind of show you the biology that's happening in your ear when a sound wave interacts with it. It's actually literally compressions in the air. So for instance, if we clap our hands, it creates a disturbance, okay? And then that disturbance goes in all directions. Now, things that go in all directions, all waves, and I think that one of the videos we looked at recently talked about this, if something travels in all directions, it gets diluted. It's like if you're standing too far away, you can't hear my clap. Okay, closer up, you hear it, far away, it's diluted. Same thing with light. If you're close up to a flashlight, you can see it. You go too far away, it's like, it's diluted. Okay, so it's kind of a function of waves going in all directions. Okay, so air is the medium, and again, if you scream in space, I hear you. One of the things in astronomy, we'll touch on a lot of different things, but it's like the beginning of the universe. So what do they call that? We made BB. Big Bang. Like this show. Okay, so the Big Bang, the initial of our universe, when there was no medium for anything to travel through, was it loud? No. And was it big? Quite frankly, yeah. Okay, so we call it singularity. So sound needs to have a medium to travel in. So you kind of see here the speaker kind of making these compressions are called the crests, and then these decompressions are troughs, crest, trough, crest, trough. So let's take a look at kind of what happens with our ears. Again, when I put together, a lot of times I'm putting together slides when I'm somewhere that I can't hear the sound, so I hope these are good. Because they did say, but is sound is here, okay? But the higher the wave means the more intense the compression, and that translates to the volume. Here in a minute, I have a slide that shows you, because they kind of talk about high frequencies versus low frequencies. Our ear obviously interprets them differently, and there is for dogs can hear things that we can't. And actually, we all have different gifts in hearing high sounds and low sounds. As you get older, you have lose some of it. And then also, if you abuse your hearing, you can sort of lose it too. So the shorter the wavelength, the higher the frequency. Remember, you're going to have to kind of have a sense for wavelength is how long it is from crest to crest, and frequency is if you're standing here, how many passes per second. So if they're short and they're traveling at the same speed, then you can get more of them per second. So shorter the wavelength, the more passes per second. What passes per second is called frequency. So the shorter the wavelength, the higher the frequency. That's how that works. And the higher the frequency, the higher the pitch. So I've got a few other couple videos to show you. So this is kind of fun. These are tuning forks, and we're going to play around. I'm not exactly sure which lab will do. So you guys have your labs on Thursday. I've got an idea, and it will have to do with sound. But here we are taking a vibration and creating a vibration within this tuning fork, and this vibration then can travel along the air here, and these are open holes. So there's an open hole here and an open hole here. You hit this, and it travels through the air, and it begins this one to vibrate. That's fun. Okay. Of course, stringed instruments are obvious. I will see the vibration. I've seen some kind of cool videos on YouTube about showing you the vibration of the guitar. This annoying person blowing a whistle here is creating vibrations through the air. Okay. This is called an oscilloscope, and oscilloscopes are great tools in physics to be able to kind of see the sound. Okay, and one of the videos I'm going to show you is what cool things you can do with sound. I've never done that with sound, but apparently, and according to the movies, it can be done. So let's take a look. Ambassadors in Cuba actually have, many of them have left because of kind of a medical phenomenon. And it was first noticed, I think, maybe this last fall, it came into the news, where people were actually getting sick at the embassy. And it was, I won't say just Americans, but we had a lot of Americans that their health went down. And they did some investigation, and they actually could detect sound that was associated with their health going south. So that, I'm like, really? So I don't know. The weapon of the future, right? Let's see. One more. I have another. Well, okay. So hertz is per second. So hertz is frequency. So for instance, if it's 30 per second, that means if you're standing here, you count 1001, you get 30 cycles, which is quite a few. But honestly, sound and then even light has really, really high frequencies. So for instance, we could get so high that we need to kind of use the metric prefixes. The metric prefix kilo means 1,000 times. So 1 kilohertz is equal to 1,000 hertz. Okay. This over here is kind of showing you in general what the human ear can hear. Remember, the higher the frequency, 20 kilohertz versus 20 hertz, the higher the frequency, the higher the pitch. Okay. So anything kind of above what the normal human ear can hear is called ultrasonic. Anything below what the normal human ear can hear is infrasonic. Not to say that we can't have sounds way up here or sounds way down here, because we can. So I mentioned the whole dog thing, and so what dog whistles do is to create something ultrasonic that dogs can hear, that people can't. I think, have we already done this? Maybe we haven't, so this is new. No, we did this, that the velocity that the wave is traveling is equal to the wavelength of the wave times the frequency, the cycles per second. So actually this is on your sheet for the test. So velocity is equal to wavelength times frequency. And I remember we did this because I kind of talked about, of course, velocity is usually, like if you're going 100 or going 50 miles per hour, velocity is usually distance per time. And if you take wavelength as distance and frequency as per time, and multiply them together, distance per time. So we talked about being able to rearrange, if this is kind of my hardcore normal relationship, velocity is equal to wavelength times frequency, we need to be able to rearrange this. If we're after wavelength, that's equal to velocity divided by frequency. If we're after frequency, that's equal to velocity divided by wavelength. So for you musicians out there, because our daughter still plays violin, but she's out of house now, but I know that her violin teacher was just really picky about me too. And is it 440? I think that's the normal A. And what that 440 means is that's the frequency of the normal pitch of an A that everybody's going to want to tune to. And I know that for musicians that are, especially if they're playing with the piano, you can't adjust the piano, but you can adjust the violin. So we would kind of double check what the piano was, and if it was at like 438, our violin teacher was so picky, she said, no, don't tune to 440, tune to 438. We love her, but she's very picky. Uh-oh, she has this recording. So anyway, in musical notes, of course, we have kind of, it goes A through A, B, C, D, E, F, G, right? No H's. And then it starts all over again. So you can kind of see here where our frequencies are increasing. This would be the next octave, increasing, increasing, increasing. This is kind of a similar look at it. But this is kind of interesting. One of the things as a musician, which one that drives me nuts, is that like an F, a note of an F on a flute is different than a note of an F on a horn. So anyway, there is a little bit of this kind of takes that into consideration. All right. This is another sound problem, so we must have done a sound problem the other day. So let's see what we can do. And then I got a little video and an assignment, and we'll call it a quit. So, consider a sound with an ultrasonic, ultrasonic. So it must be higher than a frequency we can usually hear. Ultrasonic, or we put kind of the limit at 20 kilohertz, so 32 kilohertz, that's higher, is traveling in air at 20 degrees Celsius, and it gives us the velocity. So let's see. I think I'm going to pull out, I'm going to go ahead and I'm going to say F, frequency, is equal to 32 kilohertz. Okay. Is traveling at the speed, so that's what my velocity. So I'm going to put V is equal to 344 meters per second. And what is the wavelength? So I'm going to put, I'm going to run out of room here, aren't I? I'm going to put wavelength. Remember how that works is it's kind of like a V with a tail on the top, upside down carrot sort of. Wavelength is equal to question mark. So I'm going to rearrange, I'll do it up here. I'm going to rearrange V is equal to wavelength times frequency. I'm going to solve for wavelength. So I divide both sides by frequency. So I get wavelength is equal to velocity divided by frequency. That whole algebra thing. Are there any questions about how we did that? That whole algebra thing gets a lot of us. They've been working physical science problems. Now, one thing I can see that I'm going to have to fix is that we're all about, remember you have to include the units, and you'd be like, oh, I could just plop in my velocity, 344 meters per second, and plug in my frequency, 32 kilohertz, and then divide out and I'm done. Not quite. Hertz, remember, we said just, not kilohertz, but regular hertz is per second. Yep. And so actually, we're going to have to take these kilohertz and kind of change them to just regular hertz. So help me out. So 32 kilohertz is equal to how many hertz? What do you think? A minute ago, I said 1 kilohertz is equal to 1,000 hertz. So what do you think? Yep, 32,000 hertz. And the reason I'm doing that is so that my units of the unit of the word second, time, I want seconds to cancel. So, because it looks like this. 32,000 hertz is the same thing as 32000 per second. So I'm going to do per second, so I'm going to go 1 over seconds. Now I'm ready to call what we call plug and chug. So I'm going to use this guy right up here. So wavelength is equal to velocity, which is 344 meters per second divided by frequency, which is 32,000 per second. So I'm all about letting things cancel that can. So what can cancel here? Our seconds, our per seconds. Yep. Those two will cancel, and then what units do we have left? Just the meters, yep. Very good. These cancel, and I have units of meters, which is awesome. I'm going to write down what my calculator says, and then we'll round it. Okay, so is this what you got? I got 0.01075 in units or meters. Now, we're going to go ahead and round that. When I was grading your papers, I just want to throw a few things out at you. Remember, if you round it wrong on the test, I'm not going to actually count off. What I will count off on the test is if you don't include units. Really? Okay, so make sure you include units, but rounding is. So, because I say that because sometimes when we, when we round, we actually mess it up. But if you've shown me your work, it should all come out fine. So how many digits in 344? Like in 3. Okay, this right here, actually, how many digits you think there? Just like in 2. Yep, so just 2. So 3 or 2, we have to go with just 2. So now on to our calculated value. Actually, I'm going to go from left to right, taking 2. So this one actually doesn't count. It's a placeholder. But this is the first one to count. So 0.0, this is along for the ride, it's a placeholder. This one counts, and the digit after it counts. So what do you think the answer we should report is? 0.011 meters. What do you think? They don't care what you think, it's right. So that was right. All right, so let's take a look at the other one. Now one that is not ultrasonic, but it's infrasonic. What's infrasonic mean? It's so low we can't hear it. The frequency is so low. These would be the ones that, like I said, there are military applications for these. So it's infrasonic. So I'm going to pull out, I'm going to say wavelength is 0.078 hertz, which is awesome. I'm going to go ahead and say, which is 0.078 per second, 1 over. Cool. Traveling at the same speed, so I'll pull out velocity is equal to 344 meters per second. What is the wavelength? So wow, it looks like I'm going to use the same kind of version of V is equal to wavelength times frequency. I'm going to use this wavelength is equal to V over frequency. So all I got to do is plug in wavelength is equal to velocity, which is the 344 meters per second. So what do you think is since will the wavelength, how many people think the wavelength will be longer at the lower frequency? How many people think the wavelength will be shorter at the lower frequency? It'll be longer. So we have the velocity divided by, oh, sorry, we're after, yeah. Darn it. Yeah, you guys caught it, I didn't. This should be an F for not, sorry guys. This is my frequency, final answer. I was like, wait. So velocity divided by frequency, so the 344 meters per second divided by 0.078 per second. So I changed this to an F.
Wow. So my seconds cancel out. I'm left with units of meters. And what my calculator displays is 4410.25, and then it goes on. Darn it, come back. Units of meters. So how many digits should I allow in my answer?
I have 3 here, and I only have 2 down here, because again, that 0 is a placeholder. So I'm going to go from left to right.
So I'm going to truncate it there, but I better put a couple zeros as placeholders. So what's my answer? 4400 meters.
What do you think? Have you ever been like, well, they call it, well, have you ever been in a lightning storm? And what comes first? You seeing it or you're hearing the thunder? Do you see it first or do you hear it first? It might seem like you hear it first, but actually the hearing is a delay. So you see it first and then you hear it. You might be hearing something from a previous stroke and then seeing it. But anyway, so you'll see it and then hear it. There's a delay. Exactly. And actually we can use that delay to kind of get a sense for how far away it is. The longer the delay, the farther away the lightning strike was.
Okay. Well, I've got a couple of videos I think I'll wait to probably kick off.
We have all sorts of problems. I think there's 4 out there. But you guys have these, right? Yay! So these will be due on Wednesday. Are there any questions? Okay, very good. On Wednesday we should finish up this unit and keep you posted if you have any questions. Feel free to start getting your note card ready. By probably Friday, I'll have that little review sheet I promised ready.
So that's it, man.